Good morning, everyone. In this video, I'm going to go over how to do molarity calculations with both relative and absolute uncertainty. Basically, the first thing I'm going to do is I'm going to go over the question I went over in class, and then I'm going to do a second example that will help you figure out your molarities for your titrations, right, with uncertainty involved. So let's go ahead and just review a little bit about what each of these things mean, okay? So I'm going to call this PowerPoint the relative, not PowerPoint, but video lecture versus absolute uncertainty and molarity. And I know it got a little confusing in lecture, but that's okay. Okay, so let's just recall what I told you on the very first day when we were talking about uncertainty in the lab. And in the lab, we have different pieces of glassware, like a beaker, a graduated cylinder, I just spelled cylinder with an S, sorry, cylinder, and a volumetric flask. Okay. And if you recall, I had pictures of each one of these, and in each one of these pictures, I described to you the different uncertainty that is associated with using that piece of glassware, and it actually is printed on the glassware, right? And so if you recall, the beaker had something like 1 plus or minus 5%. Graduated cylinder had plus or minus 2 mils. Okay, and then the volumetric flask had a wonderful uncertainty, very low, of 0.150 mils, or 150 microliters, right? And the thing to be clear about these numbers is that whenever you see a percentage like this, that's known as a relative uncertainty. Okay, relative. So we don't like to use relative uncertainties that much, and the reason why is because the bigger the volume, for example, you use of the beaker, the worse the uncertainty, because the percentages will go up, right? So oh, I'm sorry, I said that backwards. the smaller the volume, right, the worse the uncertainty, because as your volume gets smaller, that percentage gets bigger and bigger of that volume. So so yeah, just be aware of that. The rest of these here that don't have percentages are known as absolute uncertainties. Okay, I'm just going to use ABS for short. And so these actually can be converted in between each other by using the volume that you have, or the calculation that you're doing, and then solving for the other one. And so if you recall, in my very first uncertainty lecture, I had, for example, if you did a mathematical operation to get the value, right, the y is always the value, right up here so you remember the value, right? And if you did a mathematical operation that involved an addition or a subtraction, the equation that you would use is sy, oh, not sy, I apologize. Yeah, I was about to say sy over something, but it's not sy over something, it's just sy, right, equals the square root of SA squared plus SB squared plus SC squared, right? And so, excuse me. And so it's pretty simple to do an addition or a subtraction operation when it comes to uncertainty, and so of course the SY here then is the value for the absolute uncertainty, right? I'll just abbreviate absolute uncertainty as ABS UNC for now on, like University of North Carolina. Anyway, And then what you put into the rest. Oh, if I have to put parentheses around this, sorry. Let's put parentheses around that. There we go. So when you look at this, right, this would just be the uncertainty for the first measurement you have, absolute uncertainty, right? And the absolute uncertainty for the second measurement you have. And then this is the absolute uncertainty for the third measurement you have. And of course, you can add on as many as you want in this calculation, right? However many calculations you have, okay? Values that you have. And so that's how you would do it with the plus or minus, addition, subtraction. And then again, if you wanted to do a uncertainty of measurement for a value in which you did a multiplication or a division, right? Then that would be sy over y equals the square root of the SA over A squared plus SB over B squared plus SC over C squared. Okay? So the thing that we need to remember about this, though, is that the thing I wanted to point out anyway, right, is that SY when you solve for this right here, when you solve for this part of the equation right here, the square root of whatever, this part right here, right, the number that you get here will equal, right, when you solve for that square root number right there, the number you get right there is equal to the relative uncertainty. Okay. So essentially, SY over Y equals relative uncertainty. And that's the reason why after you do this calculation, the calculation right here with the square root of the SA over A squared plus the SB over B squared plus the SA over C, SC over C squared, and then square root it all, after you do that calculation, you still have to multiply that number, this number right here, times Y to solve for times Y right here, right, which is the value that you had to begin with the measurement, right, to solve for this, which is SY, which is the absolute uncertainty. And I generally like to see everything in absolute uncertainties. Don't leave things in relative uncertainty, right? So literally, to get a absolute uncertainty, you multiply the relative uncertainty times the value right here, right? Times the value, okay? And so what that means then is that individually, if you look at each of these terms individually, right, without the squared, just the SA over A, the SB over B, the SC over C, just those things, not with the squares, right? All of those are all relative uncertainties of the individual measurements, right? So in your textbook, they actually call, they name relative uncertainty as percent %E. So this is the percent %E of A, right? So that's the relative uncertainty of A. And then this is the relative uncertainty of B. And this is the relative uncertainty of C, right? So essentially what's happening here is for you to be able to do a uncertainty propagation on, for you to be able to do uncertainty propagation on a mathematical operation that involves a division or a multiplication, you have to take the square root of all, the square root of the relative uncertainties, right, squared plus the next one and the next one and the next one, right? So in your textbook, right, I just want to make sure we're clear, because I don't want you to get confused between what I'm telling you in class and what you're seeing in the textbook, right? This right here then, right? We can rewrite this equation, and it all means the same thing, right? And I'll keep it all together so you can see that, right? You can either say then, because these are all equivalent equations, you can either say then, for example, the percent E, right, or the relative uncertainty, right? Because by the way, remember that's the same thing as this, right? Relative uncertainty is the same thing as Sy over Y, right? Remember over here on the right, okay? Relative uncertainty is the same as that. So you can say percent E equals the square root of the percent E of A squared plus the percent E of B squared plus the percent E of C squared, right? And so this allows you to do one thing, right? One thing that might make my calculations easier. It allows you to calculate the SA over A, or the SA over B, or the SA over C first, and then plug it into these right here, right? So you have less to type into your calculator, right? If you were to type this into your calculator right here, the original equation that I gave you, that equation right there, then you'd have to type a lot into your calculator. So the percent E calculation allows you to do all the relative uncertainties for each of the one individual measurements first, and then just plug it in. But just know though that these equations right here, this one and this one, they're equivalent, right? So you could use them interchangeably too, and we're going to do that, okay? We're going to do that. You could just stick to using the original equation I gave you too if you wanted to make it, but it just makes it harder for you to type in your calculator because you have to put the SA over A for every, or SA over B or SA over C for all your measurements, right? Whereas you could just do them separately and then plug and put them in like with the E equation, but it's all the same thing, okay? So the other thing too is that I noticed the book also writes it this way too. It writes it as percent E of 4, right, which is the fourth relative uncertainty. I don't know why they say that. That's so weird. But that fourth relative uncertainty really means the actual relative uncertainty, like the total, right? It's not really the fourth, but it's the total. So make sure you know that, right? Don't get confused. You make sure you know that. And that equals, in the textbook, they write it like this sometimes too, where it's percent error uncertainty of 1 squared plus percent E2 squared plus percent E of 3 squared. And so in this case, right, the 1 right here just means A, the 2 here means B, and the 3 here means C, right? But I prefer to keep everything as letters because then it's easy to remember what you're doing, right? You can keep track of it. If everything's numbers, then how do you know the E4 is the relative uncertainty for the total calculation, right? So I'll just keep it that way, okay? So that's the basic review I want to give you, and just to clear up the difference here between relative versus absolute uncertainty, right? And you can see here, right, like for the ones that are like absolute uncertainties, right? Volumetric flasks, graduated cylinders, those things you can use to actually measure things out. You know, if you're wanting to be super accurate about it, you can use the graduated cylinder. But if you do want to be super accurate about it, you can use the volumetric flask. But I would never use something that prints on the thing prints on the glass for a relative uncertainty, because you already know that's going to be really bad. Because if you think about it, right, if you have like say if you have a 250 milliliter, right, if you have a 250 milliliter beaker, right, and you try to measure, say, I don't even know what the lines are on that. It's on a 250, I guess it goes by 50 mils. Each line is 50 mils, right? And so if you were trying to measure like 25 mils on a 250 milliliter beaker, I mean, so 1 times 25 is like a 25%, well, actually it's 5%. Wow, that's really big. So 5%. So 5% of that 25 mils that you measured could be wrong. So that's the reason why you don't want to stay away from things, right, that have relative uncertainty as their printed uncertainty, right? We generally like to stick to things that have absolute uncertainties, because on a graduated cylinder, no matter where you measure on there, it will be the same uncertainty. It doesn't matter what the volume is. And then on the volumetric flask, right, they only have one line, so that's why it's, so I use that, right? If it says it's 250, that's pretty close to 250, right? It's only off by, like I said, 150 microliters, right? Or 0.15 mils, okay? So if you have any questions, that just text me on the Teams, right? Or send me an email or something like that. But I just wanted to make sure you were clear on what the difference is between relative uncertainty and absolute uncertainty, and why we want to use either one. And then now we're going to go through how to do calculations using molarity, because they're a little bit more complicated than just doing the regular measurements, right? Because concentration units always are something over something, right? Like milligrams per mil, right? Or moles per liter, right? So it gets a little complicated. So let's go ahead. I'm gonna go ahead and redo the example that I did in class real quick, so you can see what that's supposed to be, and then I'll do another example that will help you with your titration, which I feel like I'm repeating myself, but you probably appreciate that anyway. So let's go to the next slide. That's blank. Okay. So the example I had in class was this. Okay. I had 2.634 grams, right, of NaCl, right? And this was massed out on a balance that had an uncertainty of, and I should actually write it this way, so it's correct, right? And you'll actually see it written a few different ways, but in your textbook, though, they write it this way. They'll write 2.634, and they'll go parentheses plus or minus, and then the uncertainty, and I think I put too many zeros in there. No, I didn't. 2 grams, right? And then, oh, I messed up again. So actually, I can erase this actually. Let me write that again. I just want it to look exactly like the way it looks in the textbook for you. Like this, grams, right? So that's how it usually is in your textbook. So don't worry about that part right there. So I have 2.634 plus or minus 0.002 grams of NaCl. Before I go any further with that, I just want to make clear that this number here comes from the balance, right? The balance, right? That's the uncertainty in measuring something on the balance. And so your number that you put there will be the number that you get from doing your uncertainty budget from the first lab we did, right? So it's not going to be the same as that number. It's not going to be 0.002. It's going to be something else. It might be slightly higher. So some people will actually use just the tolerances of the balance if you don't want to go through and do a proper uncertainty budget. But again, if you just use the tolerance of the balance and the linearity of the balance, or the readability of the balance, you don't take into account the human error, right, or the operator contributions to error. And so that's why we did all the uncertainty of measurement, repeating the measuring of those standard weights over and over and over again to see what the actual uncertainty would be. And so your uncertainty will be slightly higher than this, right? But for the purposes of this question, the balance's uncertainty is that, right? 0.002, which is actually pretty common. They're like 0.002 or 0.003, when you look them up in the instruction manual without any operator error. Okay, so I have 2.634 plus or minus 0.002 grams of NaCl, and I dissolve that in a volumetric flask. And its uncertainty, its volume was 100, 100 plus or minus 0.08 mils, right? Okay. So that's the volumetric flask is pretty accurate. That's very low. That's a very low for this particular volumetric flask. That's a really low uncertainty, but that's what the problem says. So we'll just keep on going. Okay, so notice then that, this is the uncertainty. Of course, we get that from the glassware, right? Printed on the glassware. And again, since we didn't actually do a uncertainty budget on those on the glassware, right? For now, in the purposes of this lab, we can just use the printed number on there, okay? Which makes your life a little easier, but just know that in real life, you're going to have to use you're going to have to actually make uncertainty budgets. So this is from the glassware, okay? Printed on glassware. Okay, so the question then is, what is the molarity? And what is the molarity? And its associated uncertainty. All right, what is its molarity and what is its associated uncertainty, right? And so the first thing we have to do is look up the uncertainties for the different elements that are involved in this formula weight, right? So I showed you that chart already in Blackboard, and that's what you'll be using to do that. And you'll use that for your lab, you do that for quizzes, you do that for the exam, everything. Don't use the periodic table anymore, unless it's the periodic table in our textbook. Our textbook's periodic table has the same numbers with the same uncertainties, right? So let's start out by saying Na and Cl, right? Because right now we're doing the what we're calling the uncertainty in the formula weight, right? Uncertainty in the formula weight. And so we know that from our textbook, and then also from that chart I gave you in Blackboard, that's the uncertainty in the formula weight for sodium is 22.989766928, right? And its uncertainty is plus or minus 0.0000 and then 0.2 grams per mole. Okay, and so remember, when you saw this in the textbook and when you saw this in the chart, right? What you saw was 22.989766928 grams, and then at the end there was like a parentheses with a 2, right? And so that 2 means that that's the uncertainty in the last digit, which means that your uncertainty will be all of the digits after the decimal point of the reported value, right? And then the last one will be the number that's in the parentheses right here, right? So that's what goes right there. Okay. So we did that already for sodium. That's good. Chlorine's a little bit easier with 35.453 plus or minus 0.002 grams per mole. Cool. Right, and then we'll just do some simple addition for the formula weight here, right? And we'll try not to mess up and say molecular weight, but the formula weight. So 58.4427928 plus or minus, right? And this is the part where we have to do our calculation. So this is an addition right here. You're adding the sodium to the chlorine right there, right? And so that means we'll use the addition equation, which is the square root of 0. Oh, I just made it short here. I usually turn numbers that are this big into scientific notation. So, but if you don't want to do that, you don't have to. 2.0 times 10 to the negative 8, right? Squared plus the other one, which is 0.002 squared. Okay, and so the number you should get from that is this 0.002 grams per mole. All right, and then so now that you see, you always round off your value, like your calculated value, using the number of digits to the first uncertainty digit, right, in your calculation for uncertainty, right? And so here we have 3 digits. Here we have 3 digits. So we'll report this number as 58.443, rounded up, right? Because the 7 rounds it up to 3. So you always ask questions about when we should round. Always round at the end of a calculation, right? And at this point, if you know everything after the third decimal point anyway is, or the third digit after the decimal point is uncertain anyway. So that's when you can start rounding. And there's this thing I like to call chemistry intuition. And as you go through I just got really blurry there. Sorry about that. I need to stop moving. My camera's like having a problem focusing on me. But as we go through your chemistry education, you'll start to get this thing called chemistry intuition, and that just comes from a lot of practice and a lot of doing a lot of chemistry. And then you'll realize when it's important to do certain things, right? Where you need to be precise about things, when you don't need to be precise about things. So, but you'll get there, I promise. Okay, you'll get there. It took me a while to get there. It'll take you a while to get there too. Some of you are actually better than me, so you'll probably get there even faster. Okay, so now that we have that, again, so just to keep everything, because the textbook likes to do it this way, put parentheses around here just so you know what the which part is the uncertainty, as if you didn't know from the plus or minus, right? Anyway, so we then know then that, because this has been beaten in your head already, molarity, right, equals the number of moles over the liters, right? And so now you just need to plug in all your relevant information to get the number of moles of sodium chloride, right? And then also calculate its uncertainty. And so we have up here the number of grams that we weighed out on the balance, right? So we'll do that first. 2.634 plus or minus 0.002, right? So remember that this uncertainty right here, it comes from the uncertainty of the balance right there, right? There you go, just so you know. And then how do we always get the number of moles? Well, you just divide by the molecular weight. I messed up. Sorry, formula weight. So divide by the formula weight. So that's the division symbol right there. And the formula weight was 58.443 plus or minus the 0.002, right? I forgot to put parentheses right there. Let me erase that. I just want to make sure that you're clear on everything I'm doing, so I'm going to erase it and do it again with the parentheses. If you want to get into the habit of just using parentheses all the time, I mean, it just makes it easier to see where the uncertainty is. But, whatever you want to do, okay? So that part right there, right, just this part right here gives you the number of moles, okay? Because you always remember the secret, right? And that's not even a secret, it's a trick. But it's not even a trick because you did it during dimensional analysis and stoichiometry, where, if you have the number of grams of something and you want the number of moles, you just divide by the molecular weight. The formula weight, right? So that gives you the number. So now we need liters. And the liters is from the flask, so we have 100 there. We'll change that to liters. 0.00, right? Excuse me, 0.0100. There we go. And then this is going to be plus or minus, right? Plus or minus. And then, it's something messy. I'm going to do that again. Now that I've learned how to erase things faster, I'm just going to start erasing things instead of scratching things out. There we go. There we go. So, and that's plus or minus. That says 8 mils, but you need that to, not 8 mils. That says 0.08 mils, but you need to change that to liters, right? And so, that in liters is going to be 0.00008, right? Liters, okay? liters. Nice. So the thing I want you to notice here, right, before we move on, is that this is in an absolute uncertainty. This is also an absolute uncertainty. And this is an absolute uncertainty. Okay? And in your book, I mean, you can do this, the next part, one of two ways. But in your book, it wants you to convert everything into relative uncertainty and do it. But again, that's because you can do all the relative uncertainties separately and then put it into your calculator. It's easier to do. Or if you're a super calculator master, just do everything in one and use the original equation I gave you with the SA over A thing. But we'll do it the way the book shows you so that it's all consistent, okay? But I just want you to know, though, these mathematically are equivalent, so don't get confused. Right, you'll be able to do this eventually at one point in your life where you see the equivalencies in all mathematical operations, and it takes a lot to get there, but you'll get there. So the next step then is to convert these into relative uncertainties. Covert? No, not covert. We're not doing. It's not a secret, right? It's not a secret. It's a convert. So the next step is to convert to relative uncertainty. Okay? Convert to relative uncertainty. And again, we already talked about it before, how to convert into relative uncertainty. It's right here, right? Okay? So if you have the absolute value, the absolute uncertainty, and you have the value you have, right? The value that you measured, you divide them by each other and you get the relative uncertainty, okay? So let's do that real quick. So I'm going to write this out like this so that you guys can see what's going on. I'm going to move over to the left because I need some room. So percent %E, all right? Actually, percent sign first and then the E. There we go. Equals SY over Y, right? And we're going to do this 3 times, okay? Because we need an SY over Y for the formula weight, right? We also need an SY over Y for the grams that you weighed out. And then we do need an SY over Y for the volume, right, in liters that you have. Okay? So let's go ahead and do this calculation then. The first one is the formula weight. So that formula weight was 58.443, right? And the uncertainty that was associated with that one was this number right here, right? The 0.002. Okay. And the next one would be the number of grams you measured, which is right here. So oops. See, I mean, I'm so glad I learned how to do erasing. Because now I can just erase it if I make a mistake. I'm even going to fix that too, because that 4 doesn't look right. No one would be such a perfectionist when I make these videos. 0.443, good. Now this was 2.634, and the uncertainty that was there for that was right here from the balance. Just happens to be the same number again, 0.002, just like that. And the last one would be the amount you measured out on your volumetric flask, which was the 0.100 or the 0.100 liters. And that uncertainty was right here, right there in liters. And so that's going to be a very long number there. Not a very long number, but just going to keep track of your zeros. And remember what I always say, I always put a space between every 3 zeros so I don't get confused, right, about how many zeros I have. So we'll go through and calculate all that out, and you get these numbers. 3.4222 times 10 to the negative 5. And then here you get 7.593, 0.144 times 10 to the negative 4. And then here you get 8.0 times 10 to the negative 4. Okay, so those are actually the values of the relative uncertainty, right? But they're not in percentage yet. How do you make them percentages? you just multiply them by 100, right? Because percentages are a decimal point that are multiplied by 100. So if you wanted to see those numbers, right, then that would be, for this one, would be 0.0034%. And then for this one, it would be 0.076%, right? And then for this one, it would be 0.08%. Okay? And so if you were actually looking at glassware or something like that, some instrument, and it were reporting a relative uncertainty, you would be using these numbers right here, right? The percentage numbers. Okay? But in our calculations, and I just noticed that some calculators don't do the same thing. My calculator does it, but some of yours do not. You could have, I thought you could have put in these percentages and just have a percent sign there. It would automatically take into account the extra zeros for the percentage for you when you do the calculation, and it doesn't. So it doesn't always anyway. And so what you're going to have to do then is, in our calculations, always use this number for the relative uncertainty. Do not use, all right? Do not use the percentage number, okay, for calcs. And I'll tell you, like, when I'm doing this for my own stuff, I get confused all the time, right? So it's really because, you know, these numbers are so small, and a couple zeros just, like, you know, can kind of get lost, and that's why I have to either I either have to convert it to scientific notation, or I have to make sure I put spaces between the zeros, every 3 zeros, to keep track. Okay. The other thing I wanted you to see too, just before we move on, is notice how the formula weight uncertainty right here, right? The FW uncertainty is super small, right? And this is like the uncertainty that's involved in calculating atomic masses, right? Because they use very precise instruments for that kind of stuff, right? Whereas in the lab, you're using just a scale or a balance, like 1 to 3 spots, and in a volumetric flask, right, that had an uncertainty of 0.08 milliliters, right? Notice how the difference between the uncertainty of using the advanced equipment that's used for atomic mass weighing, right, and then you're using glassware and a balance, your uncertainty is an entire order of magnitude larger than those that were used, the instruments that were used to figure out the atomic masses of each of the elements, or at least these two elements. So that's kind of cool. That's kind of cool to check out, right? So now that we have that, we're in the home stretch here. We're in the home stretch. So you can now do the whole percent E. Percent uncertainty. Oh, why do I do that? I put the E in the little bottom circle of the percent. Percent E equals the square root of this number right here, right? This number right here. So 3.4222 times 10 to the negative 5 squared, because remember, percent E, or uncertainty, relative uncertainty, is the same thing as the absolute uncertainty divided by the value, plus the square, the one for the grams, which is 7.5930144 to the times 10 to the negative 4. Right, gotta go slow, so you gotta make sure you get everything. Okay, actually got that. Okay, and then plus, don't forget to square that, and then plus, I ran out of room, so I'll just move down a little here. The square of 8.00 times 10 to the negative 4 squared. Right, so that's the whole thing there. So that should get you to a percent E equals, where's it at? Oh, there it is. That should get you to a percent E of 0.0011039, right? Oh, I forgot to put the E there. percent E equals that, right? Or if you wanted to report it as a percentage, it would just be 0.11%, right? But again, you only use these numbers right here, the non-percentage numbers for your calculations, because for some reason calculators don't know what it means to put a percent sign somewhere. So just use those numbers, okay? So cool, now we have a percent E, right, or a relative uncertainty. But the thing is though, we need to have absolute uncertainties in the end, okay? So how do we convert back to an absolute uncertainty? Well, same equation again, because remember, right, I didn't write it on this page, but I'll write it again just so you know. Percent E equals SY over Y, okay, right? And so you could just write it this way, right? Where, because remember, to get the absolute uncertainty here, right? Right? You just multiply this by this. Multiply the percent E by the value, right? So then percent E equals SY over Y, which is the looking for it somewhere. Oh, that's because I never did it. So sorry about that. We still need to do this part here because we haven't figured out what our Y is. Our Y right there is actually the molarity, but without our Y is the molarity without the uncertainty in it, right? So that's really simple though, right? Just do the I'll just do it really small over here. So molarity. Oops, that's an eraser. Molarity equals 2.634 divided by 58.443, all divided by the number of liters we have, which is 0.1. Oops, is it 0.1? I lost my train of thought. Where am I at here? Oh yeah, it is 0.1. Oh, what happened here is I made a mistake here. It's actually, I put an extra 0 in here on accident. We need to erase that. Up here is wrong, right? Because it's 100 mils, not 10 mils. There we go. And then 0, 0 right there. Okay. And I'm going to calculate that real quick. And the number is, so M equals, oopsies, lost it. Go back. Gotta go back to pen. There we go. Pen. So molarity is equal to 0.4507. Okay, so we could have done that before we actually went to do the convert the relative uncertainties. I just forgot. So I'm gonna move that relative uncertainty thing that I wrote there, right? And I'm gonna rewrite this higher. M equals 0.4507. There we go. And then I'll just rewrite here, convert to okay. And so after you do that, convert to relative uncertainties is where you come down and start doing this stuff here. So this is all this stuff here is. All that stuff there is conversion to relative uncertainty. Okay. All right, so now that we found this number, sorry about that, I forgot to do that. Okay, so now we put I don't know why I put %e twice there. I should have just put the number there. So let me erase this. So we're solving for the absolute value, or the absolute uncertainty. So that would be the 0.0011039. Okay. And then, which I don't even think you really need all that 39 down there. It's really small. But I'm gonna do it anyway, because I always like to wait till the end to round. And all that equals SY over the 0.4507, right? And so you just solve for SY to get the absolute uncertainty. And so now your answer here will be whatever this times this is, right? And so SY equals approximately, or the number you'll get is going to be 4.975 times 10 to the negative 5, right? So if you get rid of the scientific notation, what you'll actually get is 0.0004975, right? And then again, you always go to the very first non-zero digit of the uncertainty right here, right? And so what you use is the 0.000, and so the 9 will round it up to 5. And so now that's your SY, or absolute uncertainty, right? And so your answer for this whole problem will be the concentration of sodium chloride. By the way, if you didn't know that, brackets mean concentration, right? So you can use that as a shortcut instead of saying writing out the word concentration, just put the brackets around the formula equals the molarity that we calculated above, right there, 0.4507, and then plus or minus, and of course don't forget to put the parentheses there, because that's what your book likes to do. Okay, 0.0005. And what's the unit? Molar, right? And so that is your answer for this. Okay. So I mean, these are long problems, I know, and that's the reason why quizzes and tests are like one question, right? Or the exam will probably have 2 questions on it, or your quizzes have only been 1 question. It's because these are very long problems to do. These are very, very long problems to do. And so I totally get it. So I just looked at the recording, and it's already at 48 minutes. So I'm going to go ahead and stop this one. And I just realized that my head is blocking the the view that you have there. So I'm going to move my head so you can see. And yeah. So I hope you got all that I didn't say there. I'll just say it again, just in case you didn't hear what I said, since all that stuff was blocked. So when I calculated the absolute uncertainty right here, right, for SY, right, solve SY for absolute uncertainty, not of. Solve SY for ABS uncertainty, right? Because that's what ABS uncertainty is, or absolute uncertainty is. It's SY. The number I got was the 4.975 times 10 to the negative 5. I just converted it from scientific notation to floating decimal, right? So that made it 0.000495, 4975, right? And then remember, we always round off to the last uncertain digit, which is the 4 there, and since it was a 9 after the 4, we round up to the 5, so our new number now is 0.0005. And then I just wrote out then the concentration of NaCl using concentration brackets, right? Using concentration brackets is what I used for a abbreviation instead of having to write out the word concentration. And then, so the concentration of NaCl is the 0.4507 plus or minus 0.0005 molar. Okay? All right, so like I was saying, I just looked at the video and it's already 50 minutes long for this one right here. So what I'll do is I will stop this video and go ahead and post it, and then I will post a second video for the doing a molarity calculation with uncertainty for data that comes from a titration, and that will be in a separate video. Okay, if you have any questions, Teams me, send me a DM on the Teams, or come by the office. I'll be here all day today. You do have an exam on Monday, but I will see you in the next video. All right, thanks.